Hello dear students. So after going through the general terms related to coordination compounds, now we will discuss about the first step in the bonding of coordination compounds. Okay. When the compounds of cobalt chloride were treated with ammonia, so various types of colored species were obtained between these two. The reaction was between COCl3 plus NH3, right? So one compound that was found, it was COCl3.6 NH3. Its color was different, reddish one. COCl3.5 NH3, it was bluish, whereas COCl3.4 NH3, it was greenish in color. Now, why the color change was there? Okay, so first attempt in this regard was carried out by Werner, and he has also got Nobel Prize for that. So we will go through this theory, Werner's coordination theory, right? Now the main postulates of Werner's coordination theory. He was Alfred Werner. The first postulate was the central metal atom or ion, right? I think now you remember central metal atom or ion in a coordination compound exhibits two types of valencies. Very important. These were primary and secondary valencies. This was the first postulate given by Werner. Then primary valencies are ionizable. I think if you remember that coordination, the whatever species is written outside the coordination, for example Cl3, CO, NH3, 6 times, if we take this. So this Cl3, this is primary valency, and this is ionizable and correspond to the number of charge on the coordination ion. So if we remove this, for example CO, NH3, 6, what will happen? If 3 Cl are removed, it will be 3 positive. So it will be equal to the charge on the species, complex ion, right? Plus 3 Cl. Okay. Then secondary valencies correspond to the valencies that a metal atom or ion exercises towards neutral molecule or negative ions in the formation of complex ions, right? Now secondary valencies, it is referred to this ligands, number of ligands which are forming, how many coordinate covalent bonds are formed with the central atom, right? So these may be neutral or they may be negatively charged. This will give us secondary, or we call them as secondary valencies. Okay, we will take up each one of these in detail. As per the first postulate, the central metal atom or ion in the coordination compound exhibits two types of valencies, primary and secondary valency. Now this is a coordination compound given general, in which central atom is M and then the ligands are attached. But can you see that there are two colors of these ligands? The greenish one represents the secondary valencies, where the bluish one, they will represent the primary valency. They are represented by, primary valencies are represented by dotted lines, whereas secondary valencies by dark lines, right? As shown in this, ligands linked by primary valency, they are represented like this, M, metal and ligand. Ligands linked by secondary valency, they are shown by this solid bond. And ligands linked by primary as well as secondary valency, sometimes that ligand can show both the valencies, it will exhibit, or center metal atom, it satisfies both the valencies, primary as well as secondary valencies. So it will be shown by dotted line to one side and the dark line to the other side. That means that ligand which can satisfy both the valencies may be present within the coordination sphere. Primary valencies are ionizable and correspond to the number of charge on the complex ion. For example, in this diagram you can see that central metal atom is attached with 6 plus 3 different ligands. Green one, which represents the secondary valency, they are shown by dark lines, right? And 3 dotted lines are, these are primary valencies. Ligands are shown by secondary, green one, and the blue one by primary valency, right? Now you can see the change from this figure to this, that in case these bluish one, that is primary valencies, they are ionizable, means the bond has cleaved and they are moving away. And once the primary valencies ionizable part, it goes off, what happens? The central atom acquires the charge, right? And it corresponds to the charge. For example, in this case it is 3 positive after 3 negatively charged ligands or primary valencies, they are removed. Okay, we will take up some other examples. For example, in case of simple salts, as you can see, barium chloride. This barium chloride, it will ionize as Ba2 positive plus 2 Cl negative. So in this case, Cl negative is the ionizable part, right? In the same manner for CaCO3, CaCO3, it will ionize as Ca2 positive plus we will get carbonate ion, right? In the same manner, MgSO4, so MgSO4 will dissociate as Mg2 positive plus SO4 2 negative, right? So ionizable part is there. So in case of simple salts, they get totally ionized. Simple cation and simple anion is formed. But in case of complex salts, now if we take up example of this CuNH3 4 times SO4, so what will happen in this case? So in this case, CuNH3 4 times, right? SO4, how it will ionize? So it will dissociate as CuNH3 4 times. What will be the charge? It will be 2 positive plus SO4 2 negative, right? So in this case, primary and secondary valencies. What will be primary valency? Primary valency is this SO4 and it is ionizable part, right? So this will be primary valency. And now the ligand which is attached, how many ligands are there? 4. So they will constitute secondary valencies. I hope it is clear to you, right? In the same manner, for this chromium, NH3 6 times Cl3. So this Cl3, it will ionize as 3Cl negative and it corresponds to primary valency. Whereas NH3 is 6 times, this is 6 ligands or 6 ammonia molecules are there. So this will constitute secondary valency. Okay. Now in this third example, CONH3 6 times Cl3. Again Cl3 will be primary valency and NH3 6 times will be secondary valency. I hope it is clear to you. The same example you can see in this COCl2 is there. So this Cl, it will ionize, this Cl will ionize, as a result this will form CO2 positive plus 2 Cl negative, right? So this is for simple species, and for complex you can see in this case cobalt is bound with 6 NH3, so this constitutes secondary valency, right? And the charge that will appear, so that will be due to removal of that ionizable primary valency, that is 3Cl primary valency. Okay. Now the next postulate says that secondary valencies corresponds to the valency that a metal atom or ion exercises towards neutral molecules or negative ions in the formation of its complex ion. Okay. Now look at this picture. Central metal atom is there. Ligands are attached. Okay. So secondary valencies. Secondary valency means ligands, these ligands, green colored ligands, which are bound with the central atom, right, through these dark lines. Okay. So they corresponds to the secondary valencies. Okay. For example, in this picture you can see primary valencies are shown in the form of ligands, blue color ligands, and secondary valencies are represented by water molecule, right. So the ionizable part will be ligands shown by L, and non-ionizable, or which will have that secondary valency, that will be water molecules. So how many water molecules are there? 1, 2, 3, 4, 5, 6 water molecules are there. Okay. For the complexes such as metal ions, for these metal ions, do remember that secondary valency or coordination number, cobalt 3 positive, means cobalt forming salts in 3 positive oxidation state, will be, its secondary valency will be 6. In the same manner, platinum 4 positive salts, they will have again 6 as secondary valency. Fe3 positive ions will also show plus 6 or 6 valency or secondary valency, or coordination number will be 6. So for these three, most commonly the coordination number is going to remain 6, right. For nickel 2 positive ion, copper 2 positive ion, and platinum 2 positive ion, the coordination number will decrease and it is around 4. So 4 will be the coordination number for these ions or their salts. Okay. You can see in this example, now it's a particular example, COCl3.6NH3. Now the primary and secondary valencies are shown in this diagram. The dotted line, it shows primary valencies. That means these 3 chlorine atoms, they will behave as primary valencies, whereas ammonia molecules, they will show secondary valencies. So what is the number? What will be the charge on this complex ion? So after removal of these 3, so there will be primary valencies will be 3 chloride ions. So primary valency will be 3, whereas secondary valency number will be 6, as there are 6 NH3 molecules. Okay. The next postulate, secondary valencies are directional. Now this is very important. Secondary valencies are directional, and so as a complex has a particular shape. So that means for imparting the shape, or the shape of the coordination complex depends on the number of secondary valencies, because they have directional properties. So due to that directional properties, the complex has particular shape or geometry, right. For example, in this case, 1, 2, 3, 4, 5, 6. So there are 6 secondary valencies. So for 6 secondary valencies, the shape or geometry will be octahedral. Okay. 4 in one plane, 1, 2, 3, 4, and then pointed upward and downward. Now in case the secondary valencies are equal to 4, so there are 2 possible geometries. In this case, 1, 2, 3, 4. So it will be tetrahedral, right, or 1, 2, 3, 4. If there are 4 secondary valencies, that will depend on the hybridization state. So it will be square planar, right. So these 3 types of geometries are possible: 2 for 4 coordination number or 4 secondary valencies, and 1 for 6. Okay. Now again the same thing, showing this complex, again metal attached with the various primary as well as secondary valences, right? So in this complex you can see that CONH3 6 part, it is not ionized. That means this part is ionizable part, and this complex in this case, in this first example CONH3Cl3, it will be cationic. Okay. Whereas in this example K4FeCN6, so K4 is positive, so it will be anionic complex, right? Anionic complex is there, right? So primary valency, which one will be the primary valency? In this case, these 3 Cl3 or 3 Cl negative ions, after dissociation they will constitute primary valency, and NH3, 6 NH3, they will constitute secondary valencies. In the same manner in this complex, K4 will, it is ionizable part, or this species will dissociate as 4K positive plus FeCN6 4 negative, right? So ionizable part will be this, it will constitute primary valency, and 6 cyanide ions, they will be constituting secondary valencies. So I hope from these examples this is clear that which one is primary valency and which one is secondary valency. Now this is very, very important. In this case, 3 complexes are given. COCl3.6NH3, this is one. Second one is COCl3.5NH3, this is second, and COCl3.4NH3, this is third one, right? As you can see that all these complexes, they have different color. The first one has brownish or dark reddish brown, second one has bluish, and third one is greenish in color, right? Why there is variation, or why they show different color? Now you can see, let us focus on the first one, COCl3.6NH3. When to this complex small amount of AgNO3 was added, it was found that on treatment with AgNO3, it gives precipitates of AgCl. That is, 1 mole of COCl3.6NH3 gives 3 moles of AgCl precipitates, which was large in quantity, right? Now, on analyzing this second picture, COCl3.5NH3. Now in this case, on treatment with, when this complex was treated again with AgNO3, it has resulted in the formation of 2 moles of AgCl. That is, 1 mole of COCl3.5NH3 gives 2 moles of AgCl. The amount, the quantity of precipitates produced, they were less as compared to the first one. Okay. Now in third case, that is in case of complex COCl3.4NH3, on addition of AgNO3, 1 mole of COCl3.4NH3 gives 1 mole of AgCl. Quantity of precipitates formed was least among the 3. Okay. Now why that yield was different? So that can be explained on the basis of primary valency or oxidation number. Okay. For example, in this complex, the same complex is given CO, NH3 6 times and then Cl3. Now directly you can see that which one is primary valency or which one is secondary valency. So it's obvious that NH3 bonded with the central metal atom, they will constitute secondary valency. Whereas chloride ions, chlorine attached with the central metal atom through dotted line, this will constitute primary valency. So in old terminology, the compound was represented like this, COCl3.6NH3. But now, the new concept, the compound is represented as square bracket CONH3 6 times, square bracket close, and then Cl3. So now this clearly indicates the primary and the secondary valencies, and as a result, how many chloride ions can be liberated, or how many moles of Cl are there in this molecule, ionizable Cl. So it's obvious that there will be 3 moles of Cl. So now when this species is treated with AgNO3, what will happen? That reaction will be CONH3 6 times and it will be NO3 3 times, right? That means plus 3 moles of AgCl are produced, which will give the maximum yield of precipitates. Okay. So this is how we represent the coordination compounds now after Werner's coordination theory, and this shows that the coloration of this will be reddish brown. The same thing you can see that this compound on dissolving in water will ionize as CONH3 6 times 3 positive plus 3 chloride ions or 3 Cl negative will be written. If we represent, another example is there, COCl3.6NH3 if one ammonia is removed. So we will get the compound COCl3.5NH3. Now in this case, coordination number that is going to remain same, that is 6. But you will come to know that one of the chlorine atom, it will show both the valencies. That is, this one is primary shown by dotted lines and this one is secondary valency. So this chloride ion, it satisfies both the valency, or central atom makes the ligand to behave in both the manner. That is, this will carry that negative charge as well as it is forming that part of regular geometry. So dual behavior is shown by this chloride. Hence, what will be the ionizable part? How many chlorine will be there? So now this complex can be represented as, if I write this complex, it can be represented as square bracket CONH3, how many times? 5 times, then Cl, then square bracket, and it will be Cl2. This is how we can represent this species. And now in this case, there will be ionization will vary, and in this case there will be 2 chloride, right? There will be 2 chlorides acting as primary valency. Now just see, as that removal is done, this chlorine is behaving dually, right? In old terminology, it can be represented like this, but in new terminology, it can be represented as CONH3 5 times, then Cl, and then square bracket close and Cl2. So this is primary valency, and these NH3 plus Cl both are forming secondary valency, and such a complex is called as heteroleptic, if you remember, heteroleptic complex. Okay. Now in this case you can see on dissolving water in water, the charge that appears, that will be 2 positive. Again the coordination number remains same, that is, or secondary valencies, they remain same, out of which 5 are ammonia and 1 is chloride, right? And the 2 chloride ions, they are released. So that's why now on treatment with AgNO3, only just these 2 chlorides, they will result in the formation of AgCl. So 2 moles of AgCl are formed, whereas in previous case the number was 3, and hence the yield of the precipitate was more in that case, and here the yield is less. Okay. In the same manner for the next species, again it is, we can represent that the Cl, or I can show, for example, the complex is CO and then NH3 4 times Cl2 dot Cl. Now this is another complex and it is represented in modern terminology. It will ionize in water, resulting in the formation of CONH3 4 times Cl2 positive plus Cl negative. So it will ionize like this. And in this case, in this complex, this Cl is ionizable part, that means it will show primary valency, and NH3, how many? 4 NH3 plus 2 Cl, so total it makes 6. So 6 will be secondary valency in this case, or we can say it has coordination number, right? And now the precipitation will take place due to presence of 1 chloride. So when this 1 chloride is treated with AgNO3, so it will result in the formation of AgCl plus NO3 negative. So this AgCl will result in PPT, but there is only one AgCl. 1 mole of AgCl is produced by using this 1 mole of complex. So hence the yield of the precipitates will be least. Now the drawbacks of this Werner's coordination theory. Although it has initiated the beginning for the bonding and coordination complexes, but he has certain limitations. It does not explain why only certain elements form coordination compounds. That he could not explain. Okay. It does not explain why the bonds in coordination compounds have directional properties. Secondary valencies, he could not explain about secondary valencies. Then it does not explain the color and the magnetic and optical properties of complexes. So all these drawbacks, they were overcome in other theories, but he was the one who has initiated the bonding in complexes. Okay, this was all about Werner's coordination theory.